Today I'd like to talk about magnetic mysteries of the galaxies. So first I'll give a brief introduction and motivation, then I'll talk about magnetism and how we can observe magnetic fields, and then I'll talk about some of the discoveries that have been made possible by magnetic field studies. Our ancestors and early astronomers have been fascinated by the night sky. They have tried to make sense of the sky, figure out what the bright objects in the sky are, and how they are formed. The Milky Way galaxy that we know today was not really easy to understand many years ago. Milky Way galaxy in Farsi or Persian is called Kahkashan, or a path that the straws or the objects are spread like straws exist. And these objects are spread through this path that we can see here. If we look at the night sky today, standing on the shoulders of these astronomers, figuring out what we know today, this is what we see. So for example, here I'm showing that the night sky we would see at Stanford tonight. And here I'm using the Stellarium software. I move my cursor so you can see the bottom panel as well. This is a very cool software. I recommend you to download the software and play with it. Our ancestors have connected the brightest objects on the stars together, grouped them together, named them as different constellations, and have made different stories to convey these the knowledge that they have from one generation to another. One of these constellations is the constellation of Taurus, and in its heart there is a cluster of Pleiades or seven sisters that is cherished in many cultures and many geolocations. In Farsi, this cluster is called Parveen and has been repeated throughout history in different poetry and literature. In different cultures, or in actually many cultures, this cluster carries with itself a story of seven sisters. These are seven sisters that are the bright objects that we see with naked eyes. But actually, one interesting thing is that when we look at the sky in this region, we actually see 6 stars. So a lot of these stories say that there are 7 sisters, but one of them have gone to hiding. Norris recently published a paper suggesting that these stories that are somewhat common across cultures go back to 100,000 years. Ray gave a talk recently for the Open Cultural Astronomy Forum, which is a seminar series that I co-founded. The video of his talk is available, and I recommend you to watch it. It's very fascinating. So one of the questions that our ancestors have wondered about is, where do these bright objects come from? Many of these bright objects that we see are stars, and a pivotal question of our time is how the galaxies evolved to form clouds, stars, planets, and ultimately life. The star formation process started shortly after Big Bang and has been ongoing in the past 14 billion years that has been estimated for the age of the universe. In the past, or in the most recent 8 billion years, our Milky Way galaxy has had a relatively constant star formation rate, which is about 1 or 2 solar masses per year. So if I count the mass that is turned into the star in our galaxy in each year, we see a mass equivalent to the mass of our sun, or 2 times mass of our sun. There have been many observations to help us understand these mysteries and understanding how the stars are forming and why we have continuous star formation. We have to look at the evolution of the galaxy to formation of stars, and to understand how the planets are formed and how we end up having life on Earth. We have to understand the star formation process. And for that, let's start looking at the space between the stars. So the space between the stars contains matter in form of ions, molecules, atoms, dust grains. These dust grains are very important. They're complex and they're very useful in our astronomy knowledge. So I will come back to these dust particles during this talk. But these matter together collectively are referred to as interstellar medium. And we can say that we have not sent an astronomer to vacuum the space between the stars, so we have the interstellar medium. Interstellar medium is not homogeneous, so similar like the clouds that we see in the sky, there are regions in the interstellar medium that are denser, have more accumulation of gas and dust, and there are regions that have low density. They have less accumulation of gas and dust. And earlier astronomers have looked at these clouds in the sky, so after Galileo with telescopes, and they have given funny names sometimes to these objects or clouds that they can see in the skies. And whenever they saw fuzzy structures that they could not really explain, they called it a nebula. So I would like to invite you to post in the chat to let us know if you can guess the name of this nebula. Maybe I'll pause 1 second. So the astronomers that we use their knowledge now have given these structures or these clouds names. The name of this nebula, as you may guess, is Witch Head Nebula. And let's try another nebula. This one. Can you guess the name of this nebula? If you a puffy dress, that's a very good guess. Horsehead Nebula, exactly. So this is the Horsehead Nebula. And there are also some regions of the sky that are dark, and people before thought that these are the doorways to heaven. And they could not really explain what these dark regions in the sky are. But we know today that they are actually very cold, dense regions of the interstellar medium. So the interstellar medium and stars have similar chemical composition. So it is natural to think that the stars are formed from the interstellar medium. And you may recall the famous quote by Carl Sagan, who mentioned the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. So the interstellar medium is turning into stars and planets and ultimately life. The coldest and densest parts of the interstellar medium are molecular clouds. So these are regions in the interstellar medium that are very dense and allow for formation of molecules inside them. So if we have molecules in the interstellar medium forming, because of the radiation in the environment, they get destroyed. But in the molecular clouds, they can form and remain. because these regions are dense and they shield the outside radiation. What we know is that the stars are formed within molecular clouds. So that is known knowledge today, that the molecular clouds are the birthplace or the nurseries of star formation. So here I'm showing the Orion molecular cloud. So this is Orion A molecular cloud. This is Orion B molecular cloud. And when we look at the stars, we see that all the young stellar objects are inside these molecular regions. And these observations of the stars have been made by two very cool telescopes. So one is the ALMA telescope in Chile, and the other is the Very Large Array, or VLA. We are not always that creative with abbreviations. So Very Large Array in New Mexico. We can compare molecular clouds with atmospheric clouds. So when we look at molecular clouds, they're a lot bigger in length compared to atmospheric clouds. They can fit, for example, 100 million times the diameter of the sun within themselves. And they're a lot more massive compared to atmospheric clouds. They have a mass around 1,000 to 1 million times bigger than our sun. So technically, a molecular cloud could produce 1 million stars with the same mass as the mass of our sun. And atmospheric clouds are actually a lot denser. So I already mentioned that molecular clouds are the densest and coldest regions of the interstellar medium. However, the density of them are still lower than the best density we can achieve on Earth. So atmospheric clouds are a lot denser, and they are somewhat warmer, so 10 times warmer. Okay, so we know that it's within these clouds that stars are formed, but how? If I take a simplistic case, if I take a homogeneous cloud and I somehow perturb this cloud starts to evolve, and as the result, it forms narrowed structure. So these narrowed structure, we refer to them as filamentary structures that you can see with the yellowish color here. And what we know is that it's within these filaments that the stars are born. So the idea is that these filaments become very dense and they gravitationally collapse to form stars. So you may tell me, okay, what's very unique about these filaments? We have filamentary structures in our day-to-day life. For example, atmospheric clouds, smoke from a cigarette, steam from a cup of coffee, or a drop of ink. What makes interstellar filaments unique is that we cannot explain their formation and the lifetime that they maintain their shape in a filamentary shape without considering magnetic fields. Magnetic field is one of the fundamental forces in the universe and influences star formation. So although I explained star formation in the previous slide, using gravity or talking about gravity, what we know is that there are other characters in the star formation story, and one of them is magnetic fields that is playing an important role in the formation of molecular clouds to the formation of stars. The role that these magnetic fields play in the star formation to me is actually similar to the story of Rostam and Sohrab, two characters in the stories of Shahnameh or Book of Kings. So the relationship that magnetic field has with the star formation is very complex. We see sometimes that magnetic fields hinder the process. So they do not want to help create the stars, but at the end, they emerge as the hero of the story by rapidly slowing down the cores that or clumps of gas and dust that are turning into stars. And this slowing down process allows for formation of stars. So magnetic fields are very important in the creation of stars. However, their relationship with the star formation is very complex. And we know today that the universe is magnetized. So not only on Earth and our solar system and our local neighborhood and our galaxy, but also in the local group of galaxies and in large-scale cosmic structures, magnetic fields permeate the universe like invisible threads. And you're familiar with magnetism and magnetic fields. For example, a bar of magnets on the fridge. Or if I have a magnet bar and I spread iron filings, this is the pattern that I would get. This pattern for iron filings tells me the shape of the magnetic field. So magnetic field is a force in the universe. It means that it has a strength, the strength that is, for example, pulling or repelling the object, but also has a direction, the direction that is pulling or repelling the objects. And we know that Earth is also magnetic. So, for example, the fridge magnet that holds our shopping list exerts a magnetic field about 50 Gauss. Earth's magnetic field is 100 times smaller than that, so it's around 0.5 Gauss, so 100 times weaker. And now imagine scaling this up to the interstellar medium. When we go to the interstellar medium, the strength of magnetic field becomes a lot weaker. So the strength of magnetic field in typical interstellar medium is around 5 microgauss, so 10 to 6 times smaller than 1 Gauss. And the magnetic fields of molecular clouds are actually stronger than the typical interstellar medium. And they can be, for example, something around 50 microgauss and higher. So even though we are calling them as very important factor in the star formation process, they are not very strong compared to the magnetic field of a fridge magnet. And we need to observe these magnetic fields in 3D. So I mentioned it has a direction, so it's a vector. And we need to observe the cloud and the magnetic field in 3D. That's because if I'm an object that I can see magnetic fields, if I move along the field lines, I do not feel the magnetic fields. But if I move perpendicular to field lines, then I would feel the magnetic fields. So the direction that these fields have with respect to clouds is very important. So if I have a magnetic field here, this has a line of sight components and has a plane of sky component. When we project everything onto the sky, which is the way that we are seeing the sky, everything is like a canopy of the stars. Everything is projected onto the plane of the sky. This magnetic field here that was perpendicular to this cloud mostly appears parallel to the cloud. And I already mentioned that the orientations have important implication for how these clouds evolve to form stars. So we need to observe these in 3D, not only the clouds, but also their magnetic fields. A lot of the observations that we have made today to make our astrophysics and astronomy knowledge relies on receiving and analyzing the light. So the light that we see today is only a small portion of the electromagnetic spectrum. And you can think of light as an oscillation or you can think of light as a wave. So the more energetic waves are the gamma rays, X-rays that you're familiar with. Then we have the visible light and infrared and radio waves. For magnetic field studies, the portion from optical to radio waves have been extensively used to observe these invisible threads in our universe. And for that, we rely on a characteristic of this wave that we refer to as polarization. So if I have this oscillation in only one plane, this is referred to as being a linearly polarized light. But if I have the oscillation in so many different directions at the same time, then this is unpolarized light. And if I have an unpolarized light passing through a polarization filter, then what remains or what passes through is a linearly polarized light, if my polarization filter is a linear polarizer. And this is something that we use in our day-to-day life. So in our day-to-day life, polarization properties of light are the key to transform 2D images to 3D images in 3D cinemas, or help us block a portion of the sunlight with sunglasses, or also reveal hidden structures, for example, on the surface of a lake that we could not see without a polarizer because of the glare and the scattering of light from the surface of water. In different astrophysical phenomena, we can have polarized light produced, and the light, as it travels through this cosmic environment, the polarization properties of light changes. And by observing these changes, we can get important information about magnetic fields. So we have to find very creative ways to analyze the polarization properties of light to get information about the magnetized universe and magnetized galaxies. One of these techniques that we can use polarization properties have been used by the Planck Space Telescope, which works in the far infrared regime of the electromagnetic spectrum. And Planck telescope has observed the plane of sky component of magnetic field. So for example, here I'm showing our galaxy. The color map shows the density structure. So red shows the disk of the galaxy that is denser and has a lot more mass in a small volume. And as we go higher up, the density becomes lower, and these blue regions are lower density regions. These curved lines show the magnetic field lines projected onto the plane of the sky, as we could see with the bar of magnets in the animation that I showed earlier. So how does this work? When we have an unpolarized light from a star, and as this unpolarized light passes through interstellar dust grains, the light sees these interstellar dust grains as a polarizing filter. And as the result, the light that passes through is polarized. And by observing the polarization properties, we can get important information about magnetic field. And that's because these interstellar dust grains are elongated and they align themselves or their major axis perpendicular to magnetic field, as you can see here. I'm showing this in an exaggerated way. The dust particles are tiny in the interstellar medium, but to demonstrate what I mean, I show them in an exaggerated way. And in this technique, if we know the distances to the stars, which recent observations have helped us to understand and determine, then we can find a 2D tomography of magnetic field. So we know how the line of sight magnetic field looks like along the line of sight as we go further and further from the receiver that we have or from the telescope that we have. So this is a technique that has been used and was recently used in Doi et al. 2021 as well. We can also look at the emission from these dust grains. So these interstellar dust grains, similar to all the other objects in the universe, have an emission. So we know that we also have emission. That's how they can measure your temperature as you walk in the airport without any physical touch. So these interstellar dust grains also emit in far infrared, and because they are aligned perpendicular to magnetic fields, their emission is also polarized, and by observing the characteristics of the polarization characteristic of this light in far infrared, we can get information about the plane of sky magnetic fields. And the very first observations of this was in 1949 by Hiltner and Hall in an attempt to observe polarization of stars. So they were thinking that stars' light should be polarized, and that's why they were making these observations. But Hiltner said that no, the polarization that we are detecting is actually not due to the stars, it's due to the interstellar medium. And then very quickly, Hall confirmed Hiltner's hypothesis and said that yes, interstellar medium is magnetized, and that's why we observe polarization. And then again, very quickly, David and Greenstein explained the observed polarization by dust alignment with respect to galactic magnetic field that we already mentioned. And Spitzer and Taki explained this based on the ferromagnetic characteristic of interstellar dust grains. So here I'm showing the Orion A molecular cloud. We have observed by Planck telescope the plane of sky magnetic field of this cloud. The density structure or the density is shown by the color map. The red shows higher density region, so this is the dense molecular cloud. And the curved lines show the plane of sky magnetic fields. Okay, so this is fantastic. We have plane of sky magnetic fields, but they mentioned that we need 3D magnetic fields. How can we get magnetic fields that are along the line of sight? So their direction that is pointing is along the line of sight. One technique that allows us to observe the line of sight magnetic field is Faraday rotation. So Faraday rotation is also using the polarization properties of light. So if I have a wave again, so imagine that I'm oscillating a rope up and down. So I have this wave. As this wave is traveling through the interstellar medium, the orientation that is oscillating rotates. So the polarization properties of light rotates. And by observing this, the amount of this rotation, we can observe or get information about magnetic fields. However, probing magnetic fields of molecular clouds using Faraday rotation was once considered impossible. My team and I developed a technique for determining the line of sight magnetic fields of molecular clouds. So not only we showed that it's possible for molecular clouds, we developed a new technique based on Faraday rotation to get magnetic fields of molecular clouds. And we've With a number of excellent students, we've also developed software that is available publicly that can infer the line-of-sight magnetic fields of many molecular clouds. So now using Planck's plane of sky magnetic fields and line-of-sight magnetic fields, we can get 3D magnetic field information. Here I'm showing the line-of-sight magnetic fields at circles. Red shows magnetic field pointing away from you, and blue shows magnetic fields pointing toward you. And if we look carefully, we see that at one side of the Orion A cloud, magnetic fields are predominantly pointing away from you. And at the other side, they're predominantly pointing toward you. So this is a very interesting feature of magnetic field associated with this molecular cloud that we also see it in another cloud. Here I'm showing the Perseus molecular cloud, which is in the Perseus constellation. And the line of sight magnetic fields are shown again with the circles. And we see at one side magnetic fields are pointing away from you, and at the other side of the cloud, they're pointing toward you. And we were able to reconstruct the 3D magnetic fields of these clouds. So for example, for the Perseus, if I show it in a very simplified cartoon, so this is the molecular cloud, narrowed, elongated structure. What we found is that magnetic fields are concave from our point of view and point in the decreasing longitude direction. And the cloud, what we know of its 3D structure is that it's parallel to the plane of the sky. So I chose this cloud to talk about because it's simpler to talk about. What we have found is that the same way that the footsteps in the snow tell us about the path that a person has taken, magnetic fields, these invisible threads, reveal the history of these structures. So they can tell us how these clouds were formed and were evolved, and they can also reveal the future too. So they can tell us the direction that these clouds are going to. So they can tell us how these clouds evolve to form stars and planets. So the research that my team and I have carried out has shown that through 3D magnetic field observations, we can explain how the clouds are formed and how they evolve. We can also identify galactic and cosmic regions that are not detectable in traditional total emission observation. So the same way that we see with our eye, if we don't have any polarizing filters, we could not see what the lake has underneath the surface. But when we have a polarizing filter, we can see the cosmic structure, or we can see the lake underneath the surface of the lake. And in this case, we can see the cosmic structures that we could not see before. So an example to this is a new structure that we identified in the Perseus cloud. So the formation of Perseus cloud was previously explained by an energetic bubble that exists in this region. So this bubble is actually right now not very energetic, but it was produced by many energetic events like supernova as a shell that interstellar medium is accumulated on. And these events allowed for formation of Perseus. That was what was believed. We also see the Taurus molecular cloud, which is in the Taurus constellation. Using the 3D magnetic fields of the Perseus, I propose that there must be another structure, perhaps behind the Perseus cloud, that has interacted with this cloud and has shaped the magnetic fields further in these regions. in this region. So we don't know how this structure looks like, how big it is, but we know that there is something present there, or there was something present at some point there that has influenced the formation and evolution of this cloud. And after we proposed this, very quickly, this was confirmed using follow-up kinematic observations, so observations of the speed that we see in the interstellar medium and the stars. And this is actually consistent with theoretical cloud formation models. So one model is cloud formation of Inutsuka et al. 2015, where bubbles or energetic events result in creation of dense structures, and they actually suggested that we need multi-compression by different supernovae, for example, to form these clouds. One supernova event is not enough to form these clouds. And as the result of this theory, one of the predictions that this theory has is that we would have these curved magnetic field lines. So both our cloud formation model and the field lines that we observe are consistent with this cloud formation model. And we do see this in the interstellar medium too. When I showed an earlier simulation, I said that if I have a homogeneous cloud and I perturb the cloud, it starts evolving stars. So one way that we can perturb this cloud is by energetic events, by, for example, stars. So stars, not only we have their formation from interstellar medium, but also they result in the formation of molecular clouds too. So it's a cycle. We have molecular clouds forming, then stars forming, and then these stars result in the formation of new molecular clouds that we can see here, and formation of new stars. Okay, so we have these 3D magnetic fields. We know how these clouds are formed, but we can also explain how these clouds are evolving based on their magnetic field morphology. And to explain this, let me talk about another cloud, which is called as NGC 6334. It's a massive star-forming cloud in the disk of the galaxy and has a lot of bright stars. When we look with the Planck telescope, the plane of sky magnetic fields look something like this. They look perpendicular. But we want to look at the evolution of the cloud. So we want to increase the resolution that we can have. So for example, when you make an image with your camera and you want to see the image better, you use a better camera with better resolution. So for this, we use James Clerk Maxwell telescope, which is located in Hawaii and works in similar frequencies as Planck, so in far infrared regime, and allows us to observe the plane of sky magnetic fields. And these lines, the orange lines, show the plane of sky magnetic fields of this cloud. And the background shows the molecular cloud as well. And these magnetic field lines are similar to the iron fillings patterns that we talked about. And when we look, we see that it's not, largely it's consistent with Planck, but we see a lot of details that we could not see before. For example, here we see a circular pattern in magnetic field lines. And what we know about this region is magnetic fields are actually pushed by energetic events as a result of massive stars activity here. So here we have a massive or a series of massive stars that have created a bubble and have pushed magnetic fields. And my student Kwai Spiller have been working on developing computer vision algorithms that we can detect these patterns in the interstellar medium using magnetic field observations. Okay, So you may ask me, so have we solved all the mysteries? Do we know the magnetic field mysteries of our galaxy now? No, we don't. These are only a few cases, few specific cases for clouds that may be in different environments than many other clouds in our galaxy and in external galaxies. So we need a lot more observations, and we are lucky because we are in an era that new telescopes, new exciting telescopes are being built. One of these is the Square Kilometer Array Observatory, or SKAO. And it's a radio observatory being built in South Africa and Australia, and consists of many fully steerable dishes and also dipole antennas. And it can observe the Faraday rotation that I mentioned, not only in our galaxy, but also in the cosmic web that is connecting the galaxies together and in external galaxies. So with these, we will be able to solve mysteries that are still remaining today. But we also need plane of sky magnetic fields or far infrared observations. And one telescope that is being built currently in Chile is the Fred Young Submillimeter Telescope, or FEAST. And within CCAT Prime collaboration, we've secured time to observe the plane of sky magnetic fields of many more molecular clouds in our galaxy, and also observe magnetic fields of external galaxies. And with these, we will be able to reconstruct 3D magnetic fields of different regions. And one telescope that I'm very excited about is the Dragonfly Telephoto Array in optical and near infrared, functioning mainly in optical regime or optical portion of the electromagnetic spectrum. So Dragonfly consists of many commercially available Canon camera. A survey is currently being carried out by 48 of these cameras. And right now it is not equipped with polarimetry, so it cannot observe the polarization properties of light. So missing some information that we can gain from our universe. So I have been working on adding polarimetry to this telescope. So here is a setup that we have in the lab in collaboration with the Dragonfly team and Leo Holberg, an optical physicist at Stanford. This shows one of the camera, one of the setups that we have. And with this, we would be able to answer many questions, not only about the 3D magnetic fields in our galaxy and external galaxies using starlight polarization, but also the 3D structure of the galaxy. We can reveal and help answer questions about the early universe and also help find dark matter signatures. And we now have telescopes and tools that early astronomers could not even dream of, and we can see the invisible threads that are not really invisible to us anymore, but they were invisible to ancient astronomers that have helped us shape the knowledge that we have today. So in summary, the universe is magnetized from the cosmic web that connects galaxies down to formation of stars and planets. Everything is magnetized. And these magnetic forces, together with other forces, guide the cosmic dance of gas and dust that allows for formation of stars and planets. And we have built and developed new techniques that reveal the three-dimensional magnetic fields of interstellar medium. And with these, we've been able to explain cloud formation and evolution. And looking ahead, we have exciting telescopes coming that will help us reveal the invisible threats from cosmic waves to star formation. And with the Dragonfly telescope, we will also be able to answer fundamental questions about our universe that we were not able to answer if we equip this telescope with polarimetry. So I'm working on securing funding so we can equip this telescope with polarimetry. And if you would like to hear more about Dragonfly or to ask how you can support us more, please don't hesitate to let me know. And with that, thank you so much. I'm happy to take any questions.
Thank you so much, Dr. Tahani. That was great. Thank you for sharing so much information. We do have several questions I'm going to try to get to. The first one is very simple. Can you share the name of the software you mentioned early on that you recommended people play around with, and we can share that?
Yes, absolutely. It's called Stellarium. I'll post it in the chat. And it's available. You can download and install it.
Excellent. Thank you. Another viewer says, thank you for the amazing talk. I believe this was earlier on in your presentation. They mentioned the original image you showed of the molecular cloud as a dark region. How do astronomers then see the birth of stars in these regions?
So I assume Den is referring to now this, like, or over the history. So initially, with the theory of gravity, people thought that the stars should form as the result of the gravitational force that we have. And when we look at these dark regions with optical telescope, we see them completely dark. But when we look at these regions with far infrared or radio telescope, we see the hidden structures that are there. So we see the molecular clouds, we see all these structures. And we see that these are denser regions that allowed for formation of stars within these regions.
Great, thank you. Another viewer asks, how much is known about the origins of cosmic magnetic fields? Is it all a result of the Big Bang, or are there other factors?
That's a great question, and that's a question that we do not know. So that's an active area of research by looking at magnetic fields of interstellar regions and the halo of the galaxy and external galaxies and the cosmic waves. We are hoping to answer that question.
Great, thank you. Another viewer writes, thank you so much for the great talk. Does the information of polarized light we get from the sky change as it enters Earth's atmosphere or by Earth's magnetic field?
Absolutely. Yeah, that's another excellent question. It does, and we have to, depending on the technique that we are using to observe this polarization. Some techniques are sensitive to the atmosphere, and we have to constantly monitor the atmosphere daily. So it does, and that's something we're aware of and monitor and can calibrate well.
Thank you. Is AI able to assist meaningfully with data analysis, or the physics of it too complicated?
Absolutely, yes, it is. And it's a new, well, not so much new, but in astrophysics, it's relatively new, and it's being used and explored in very different areas of astrophysics. And we are hoping to answer questions that we cannot answer with AI. So it is definitely helpful, and we are trying to keep up with all the new exciting AI techniques to help address questions that we could not address before.
Thank you. So many questions coming in. Another viewer writes, Earth's magnetic field protects it from harmful cosmic radiation. Are we able to observe similar effects in other planets using the techniques you've described?
Great question. These are all very great questions. In terms of other planets, similar phenomena should be going on for other planets. I am not aware of magnetic field observations to the scales that we have for the Earth that we know of for other planets. But this is a common mechanism that could be ongoing for other planets as well.
Thank you. How hard is it to differentiate an effect of gravity from an effect of magnetism?
Great question. So by observing the strength of magnetic field, we can calculate the energies and the pressure from magnetic field on the gas and dust in the region. And for gravity, also by observing the densities of the structures, the mass of the structures, we can calculate the energies and the pressure that that gravity exerts onto regions. And we can compare these to, a lot of times we see that they are they have somewhat similar energies, but a lot of times we see they have different energies. For example, when I showed the bubble and the magnetic field were tangential or circle around the bubble, we see that magnetic fields are not energetic enough to stop this outflow, but they are actually shaped by this outflow. There are other regions in that cloud that I did not talk about that we see magnetic fields are governed by the gravity. And there are other regions in that cloud that we see magnetic fields are governing the motion of gas and dust. So it's a game between all these forces in these regions, and we have to constantly calculate, study, and explore.
Thank you. What makes radio telescopes special in studying the magnetic fields?
Radio telescopes are very exciting for different reasons. So the Faraday rotation that I talked about cannot be really seen by optical telescopes or even with far infrared telescopes, because for Faraday rotation we need lower energy wavelengths or lower energy wave or higher wavelengths. So they allow us to observe Faraday rotation that are invisible to other telescopes. They also allow us to see atoms and molecules in the interstellar medium that we cannot see with optical telescopes. For example, the dark heart-shaped cloud that I showed earlier, when we look with optical telescope, we don't see anything because the cloud is scattering the light from the background stars. But when we look with radio telescopes, we can see the molecules in that region and see the cloud structure. So they reveal a lot of information. These are just two examples. And each of these telescopes in each of these wavelengths reveal something that the other cannot. So we need to have multi-wavelength observations from X-ray and gamma ray to radio.
And how does magnetism help explain the interaction of dark matter and dark energy with ordinary matter?
Great question. So there, I'll mention that my area of study is not dark matter. What I know is that there are different theories that say that the dark matter cannot really interact with magnetic fields. So there may be no interaction, but we don't know much about dark matter. So this remains an open question.
Okay, keeping an eye on the clock, maybe last question. Viewer asked a two-part question. How does magnetic fields act at the edge of the expanding universe? Where is the end of space or the universe? And does the study of magnetic fields help to understand it better?
Great question. That is a question we are trying to answer. I don't have anything more to say at this point, but that is an open question. It's an exciting question.
Wonderful. I think that's a great place to wrap up. Thank you so much, Dr. Tahani. It was wonderful to host you and learn more about your work here at Stanford. For everyone who is asking, the session was recorded and will be shared later. We look forward to hearing more about your work. Have a good
Thank
day.
you so much, Rama.